Hello everyone, welcome to this session. From this week, we will talk about the particle swarm optimization. And this session, we will provide a first introduction. The first question to talk about is particle swarm optimization. So what is a swarm? Right, this is an important question. So a swarm is a collection of individuals, and they are interacting and they are neighbors. So in the nature, there are plenty of them. So for example, the fish colony, a group of fish, and a bird colony, a group of birds. We can see fish, birds. In these groups, there are intelligence. So that's what we call it a swarm intelligence. So why there is intelligence? Because we observed that the fish gathering in a group can effectively find food compared to one fish, a single fish. The reason is what? Because any fish who finds the food, it can drive the whole fish group to the food because they interact with each other. So we can see that it's like this. So here is the food, and there are many fish. So one of them find it first, while the others will follow it to find the food, right? So this we call it the fish feeding model. In the fish feeding model, we can extract some intelligence that can help us to develop optimization techniques. So, for example, if we find food, this is the optimal solution, right? The food is located in the optimal solution, and the others are drive to it. So what are the intelligence we can find from it? So first of all, there is a swarm, right? So the swarm is formed by multiple individuals, not a single one. So there is a population. The second, not only a population, the members or individuals in the population must help each other. So it means they can interact with each other. So with these two ideas, we hope to generate some optimization techniques based on the swarm intelligence. So in this way, we proposed the particle swarm optimization. So this algorithm was proposed by Kennedy and Everhart in 1995. This algorithm simulates the flight and foraging behavior of birds in group. And nowadays, PSO is very popular used, especially for continuous optimization problems, and there are different versions. So we call them PSOs, like GA. Okay, so now we have the particles, and they interact each other, and they move, right? So we can consider the particles as what? As solutions of the optimization problem. So here I put an example. If there are two dimensions, x1 and x2. So we can see each particle, we have a certain x1 value and a certain x2 value. So these are the solutions, right? Solution space of an optimization problem. And these particles move so they can arrive to better solutions, right? So for a particle, the two properties that we need to pay attention to is a position and velocity. Position and velocity, right? These two are important. One of them represents the location, that is the solution. And velocity, it shows that how this one can move to a better place. Based on this idea, we can build an algorithm, so we can do the following steps, right? It's population-based. We can first initialize a group of random particles, and each one have the two properties, has its position and its velocity. So this one can be randomly assigned. Then we need to find the optimal solution. Iteration by iteration, the positions keeps improving, right? So how to improve it? We need to borrow ideas from the interaction of the fish, right? So we need to update the particles by tracking two extreme values. But these two extreme values are what? Are the fish who find the food, right? So these two extreme values, we call it P-best and G-best. So what are they? P-best is the best position of the current particle. So for example, the swarm have 50 particles, right? And we have 30 iterations. So in each iteration, the particle 1 have a different position, right? So for example, in iteration 3, we can find in the 3 steps have 3 positions, which one is the best? And this one is the p-best, the current best position of the particle. So g-best is what? Is the best position of the whole population. So for example, in iteration 1, the 50 particles in the swarm, each one have its position. Then the current best one is a g-best. In iteration 2, the 50 position change, there's another g-best. So these two also keeps updating, so all the other particles will chase them, right? Will chase that. So this means the other particles are attracted by them to find the food, right? So this is the general ideas of PSO. So based on this, we can have a working flow of PSO algorithms. First, we do a initialization. Then we evaluate the p-best for each particle. So in each iteration, we have the particle's position, and we can evaluate the p-best. Then we can update the g-best of the population. Now we get p-best and the g-best. Based on them, we can calculate the velocity of each particle by some sort of formulas, right? So based on this velocity, we can update each particle's position to get its new position, considering this velocity and the current position, right? So if the termination conditions has not been met, we go back and iteratively carry out these procedures until the termination condition is met, and we have the optimal solution, right? So this is the basic workflow of the PSO algorithms. So later we will discuss the details step by step. So that's all for this session. Thank you very much. Bye-bye.